Aside from these limit laws, we also have to take notes about infinite limits and limits at infinity.
Let's start with those having vertical asymptotes. Let's try to evaluate the limit of 1 over x cubed as x approaches 0 from the right. Looking at the graph of the function 1 over x cubed, as x approaches 0 from the right, the graph increases without bound. Do you think the graph will cross the y-axis? Definitely not, because when we substitute 0 to x, the function is not defined. It will just be closer to the y-axis as we choose a value that is closer to 0 from the right. So we say that the limit of 1 over x cubed as x approaches 0 from the right is positive infinity. Try also evaluating the limit of 1 over x cubed as x approaches 0 from the left. Based on the graph, as x approaches 0 from the left, the graph decreases without bound. That means that if we substitute a value that is closer to 0 from the left, the result will become smaller and smaller but will never be 0. Hence, the limit of 1 over x cubed as x approaches 0 from the left is negative infinity. Now consider the limit of 1 over x squared as x approaches 0 from the right. Using the graph of 1 over x squared, we can conclude that the limit of 1 over x squared as x approaches 0 from the right is positive infinity. We will also have positive infinity for the limit of 1 over x squared as x approaches 0 from the left. Take note that as x approaches 0 from the left, the graph increases without bound. Hence, the limit of 1 over x squared as x approaches 0 from the left is positive infinity. With these, we can derive the laws for infinite limits. If r is any positive integer, then the limit of 1 over x raised to r as x approaches 0 from the right is positive infinity. On the other hand, if we have 1 over x raised to r as x approaches 0 from the left, there are two conditions to take note. If r is even, the result is positive infinity. If r is odd, the result is negative infinity. It is also important to note that when the function is rational, we can also see that its graph has a vertical asymptote, just like the graph of h of x equals the square root of 2 plus x all over x. The function is asymptotic to the line x equals 0. With this, we can only evaluate the limit of h of x as x approaches 0 from the left and the limit of h of x as x approaches 0 from the right. Based on the graph, we can say that the limit of h of x as x approaches 0 from the left is negative infinity. On the other hand, we can also say that the limit of h of x as x approaches 0 from the right is positive infinity. From the given, we can derive the following laws. If a is any real number and if the limit of f of x as x approaches a equals c, where c is a non-zero constant, and the limit of g of x as x approaches a is 0, then we have four conditions to take note. The first two deals with c is greater than 0, while the last two deals with c is less than 0. If c is greater than 0 and g of x approaches 0 through positive values, the limit of f of x divided by g of x as x approaches a is positive infinity. However, if g of x approaches 0 through negative values of g of x, we will have negative infinity. For c less than 0 and g of x approaches 0 through positive values, we shall have negative infinity. On the other hand, if c is less than 0 and g of x approaches 0 through negative values, we will have positive infinity. However, these conditions hold true if x approaches a is replaced with either x approaches a from the left or x approaches a from the right. Now let's verify our answer a while ago. Let's start with the limit of h of x as x approaches 0 from the left equals negative infinity. We evaluate the given function. We assume that f of x is equal to the square root of 2 plus x and g of x equals x. Evaluating f of x at x equals 0, we will have square root of 2. Take note that c is equal to square root of 2 and that it is greater than 0. When g of x is evaluated at x equals 0, we will have 0. But take note that g of x approaches 0 through negative values. So from the given four conditions, we are going to use condition number 2 since c is greater than 0 and g of x approaches 0 through negative values of g of x. Therefore, the limit of h of x as x approaches 0 from the left is negative infinity. Let's also verify our answer for the limit of h of x as x approaches 0. Again, we assume that f of x is equal to the square root of 2 plus x and g of x equals x. We evaluate each function at x equals 0, so we will have the same results. C is equal to square root of 2 and that it is greater than 0. And then evaluating g of x at x equals 0, we will have 0. Remember that g of x approaches 0 through positive values. With these, we are going to use condition number 1, where as c is greater than 0 and g of x approaches 0 through positive values. Hence, the limit of h of x as x approaches 0 from the right is positive infinity. Let us also explore the limits at infinity. Remember that positive infinity and negative infinity are not numbers that we can use to replace x. Negative infinity means the value decreases without bound, whereas positive infinity means the value increases continuously or also increases without bound. In infinite limits, you have learned that the value of the function decreases or increases without bound as the independent variable approaches a certain number. Now, what if these conditions were exchanged? Meaning, the independent variable either decreases or increases without bound. Consider the limit of 1 over x cubed as x approaches to positive infinity. Using the graph of 1 over x cubed, notice that as the value of x approaches positive infinity, the value of the function approaches 0. Looking at the graph, we can conclude that the limit of 1 over x cubed as x approaches to positive infinity is 0. On the other hand, when we have the limit of 1 over x cubed as x approaches negative infinity, the function also approaches 0. With these, we can have the following laws. If n is positive integer, then the limit of 1 over x raised to n as x approaches to negative infinity is 0. And then the limit of 1 over x raised to n as x approaches to positive infinity is also 0. Let's apply the limit laws that we have just learned. By evaluating the limit of 2x minus 3 all over x plus 5 as x approaches to positive infinity. To evaluate this, we divide each term in the given function by x. So in the numerator, we will have 2 minus 3 times 1 over x. In the numerator, we will have 1 plus 5 times 1 over x. Applying the limit laws for quotients, we will have the limit of 2 minus 3 times 1 over x as x approaches positive infinity, all over the limit of 1 plus 5 over 1 plus 5 times 1 over x. Then we apply the law for sum and difference of functions. So we will have the limit of 2 as x approaches to positive infinity minus 3 times the limit of 1 over x as x approaches positive infinity, all over the limit of 1 as x approaches positive infinity minus 5 times the limit of 1 over x as x approaches positive infinity. Applying further the law, we will have the limits of a constant will be 2, and then we will have 3 times the limit of 1 over x as x approaches positive infinity. Now remember that this is equal to 0. So we will have negative 3 times 0. In the denominator, we will have 1 minus 5 times 0. So simplifying, we will have 2. Therefore, the limit of 2x minus 3 all over x plus 5 as x approaches positive infinity is 2. Let's verify our answer using the graph of the function. Note that the function is asymptotic to y equals 2. We can trace the portion of the graph corresponding to the limit of 2x minus 3 all over x plus 5 as x approaches to positive infinity. Hence, we can say that as the value of x approaches to positive infinity, the result is 2. Now we're done with the different limit laws. Remember that we can evaluate any algebraic function, polynomial function, rational or radical function by using one or a combination of the limit laws. If f of x is defined as a polynomial function, then the limit of f of x as x approaches a is f of a. If f of x is defined as a rational function or a radical function and a is in the domain of f, then the limit of f of x as x approaches a is equal to f of a. However, if f of x is defined as a rational function or radical function and f of a is an indeterminate form, then we evaluate the limit of f of x as x approaches a by rationalizing or factoring in order to cancel common factors. And then we apply the limit laws.